In this third video segment, we are moving on with the dynamics of floating-based systems, so not only the description of the motion, but really analyzing the cause of the motion. So far, what we looked at was the dynamics equation of motion, which was m times q double dot plus b plus g is equal to torque. And then what we did is we also looked at external forces which come in through the Jacobi transpose times F. Now what we do now for the floating-based systems is a couple of changes in this. First change is that instead of q double dot, we are looking at u dots. So we are making us aware of the fact that we have one floating base which has a parameterization dependent q. So we're looking at q dot here, that this mass matrix is really universal and independent of the configuration. Otherwise, if I had here q dot and the parameterization dependence in here, I also would require this in my mass matrix. Plus b plus g, that part remains the same, but now there's one huge change to the torque. So instead of the torque, which was here just a torque vector, we have now a selection matrix for the torque, which selects these degrees of freedom which are actuated, namely the joints and not the floating base. So the selection matrix here, this selection matrix selects out of the base velocities, and the joint velocity selects only the joint velocities, which are the ones that are actuated. So in blue and red, we have now the difference labeled here. As I said, selection matrix, then these external forces here are, to a large extent, as you see later, contact forces and contact Jacobians, and then we have u and u dot instead of q dot and q double dot. So here's again an illustration of a floating-based system, in this case a quadrupedal system. It has a base, which is described by the base coordinates, so this qb for the unactuated base, and it has joints, which are these 12 joints, so 4 times 3s, which are the actuated joint degrees of freedom. If you write now the equations of motion, as I said last time, we had like mq double dot plus b plus g equals to torque, and now we move on with the fact that not all elements are actuated. So we have an unactuated base, namely that my torques do not act on these base coordinates. So I have to have the selection matrix here, which is in essence a 0 part for the base, first 6 base degrees of freedom, and the identity for the following nj joint degrees of freedom. And the selection matrix, as we have seen before, just selects the qj's out of all the q's. And here, for the first time, for simplicity, we keep this q double dot. We don't write u, but what we mean is u dot and not a time derivative of a configuration-dependent parameterization. Then we have contact forces that are acting on my system, and these contact forces, they are added through a contact Jacobian. Now there's two ways of how you visit this in the in literature. Either people write it on the right hand side, so like the taus, then this F is essentially the forces acting on our system. So similar to the taus which are acting on our system, also these forces, if you write them on the right hand side, they act on our system. If I write it on the left, then this F means that it's a force which is exerted by the robot on its environment. So these things have different signs. Obviously this Fs and diff Fs can't have the same sign, otherwise one or the other equation would be wrong. Now what I want you to learn in this class is primarily that whatever I'm doing now, whether I'm looking at the manipulator, at the legged robot, at the UAV, the equations remain the same. Really big changes are that these FS, these are for the manipulated interaction forces at the end effector. For a walking robot, these are ground contact forces. For a UAV, these are lift forces. And then S is in essence just a selection which selects for the legged robot the joints that are activated, and for a UAV the props which are activated, and so on and so forth. So these external forces, as mentioned, can come from different sources, as we will see later in the UAV and the fixed wing sections. If we have a wing, then these external forces are aerodynamic forces, which are depending on the inflow, on the profile, and on the surfaces. We can also have contacts for legged systems, and these forces are then coming from the contacts. Very often this is, in the most simple case, shown with a spring damper element that apply to this contact, which essentially says like we have a spring part, so stiffness times a position offset, and a damping part. As we know, legged robots will only exert forces when being in contact, not when lifting off. So there's no pulling force. So there's no pulling force that can apply to the system, which means we have to set it to 0 if we are lifting off, so no negative force. There is different spring models, a simple linear one. This is the one that we have here. We can also have linear ones with like a spring in series to spring damper. We can have non-linear ones, whatever. So different types of contact models which relate the position of my end effector into a ground reaction force, similar to an aerodynamic or any other force which relates the state to a force. Now, one of the biggest problems in soft contacts is that we have to trade off between what is physical accuracy, what are the actual stiffnesses and the actual damping parameters, versus what makes your simulation numerically stable. So by tuning this Kp and Kd at the contact, I can achieve various different behaviors as you see them here. And of course, the stiffer I make the system, the higher I make my damping, the more stiff my dynamics equations of motion become, the likelier it's becoming unstable, the more problematic numerical errors become, the slower my simulation will be. So that will always result in a trade-off between tuning these contact parameters to be some sort of a physical representation, but much more to become essentially a numerical tuning parameter to get a nice interaction behavior. As a matter of fact, the softness of the contact only is a function of the discretization that we're looking at. So you see here a golf ball which collides with the environment. If I look at the time discretization, which is rather large, then obviously I have almost perfect hard contact. So the ball hits the ground with a certain velocity, the velocity is reverted, it jumps off. But if I discretize it to a very small scale, I see a behavior like this, like a deformation, a very soft behavior. So it's very hard to describe this, and this would actually mean that we would have to go down to FEM analysis and simulations in order to simulate a much more complex multi-body dynamic system, which makes it just unfeasible. So in summary, soft contacts, or the choice of parameters within the soft contact, can lead to very stiff equations of motion. If you would like to parameterize this golf ball interacting with the environment, you would have to go to very small time steps, and that can really lead to numerical instabilities of your simulator. The second thing is that the contact behavior strongly depends on the robot parameters and its configuration. So for example, if I take a robot and I'm doubling its mass, then of course I have to change the contact parameters, which is kind of strange, right? The contact parameter is only a matter of the materials, but not really a matter of the robot properties. So in other words, I have to always retune parameters depending on the robot, and also depending on the configuration of the robot. So if I'm colliding with a stretched leg, which means we have a very high inertia. Obviously, high inertia means that it can lead to large deflections if I have low stiffness, while if I am completely retracted, have a very low inertia, I have completely different inertial properties at the end effector and hence different spring mass, damper, oscillation behavior. So also depending on the configuration, you have to tune these parameters. So that means that these contact parameters are not really selected as physical parameters, but rather much more as numerical parameters where we trade off stability with accuracy. An alternative way to soft contacts are hard contacts, which means that these forces, these Fn's here, they are not anymore a function of the state, but they're much more a function of a constraint. So let's have two bodies here which have a distance Rn becoming in contact. If they're closed, that means Rn is equal to 0. If they stay closed, that means this Rn dot is equal to 0. And that gives a complementary problem to the between the motion of the system, so R's, R dot and R double dot, and the contact force. In fact, what that means is that if we are closed, so if both Rn is 0 and R dot n is 0, then I have to have a Rn which must be greater or equal to 0. It can be 0, that means also in the future we're going to stay closed. If we are 0, then we can apply a certain force Fn. If we become larger than 0, then the system will separate in the next instant, which means that my force is equal to 0. So I have this complementary relationship. That means either my R double dot n is 0 or my Fn is 0, and both can only be positive. Now, similarly to a system that has soft contacts, I can also simulate a system that has hard contacts. So what you see here, for example, is a simulation of a couple of balls that are dropped to the ground on the left from certain height, on the right already on the ground, where we have different restitution parameters in that sense. On the left hand side you see that there's a hard collision where the post-impact velocity is equal to minus the pre-impact velocity. On the right hand side you have a restitution coefficient which says like, okay, they are more like sticky balls. So if they collide with each other, the post-impact velocity is getting 0. And you can see how now the simulation is similarly to changing stiffness and damping parameters by changing the restitution parameters can lead to various different behaviors. So when we calculate these external forces from the constraint, we can essentially start with the dynamics equations of motion that we introduced at the beginning. Now with this addition of this contact force, which is mapped in through the Jacobi transposed. As you know, the points that are in contact must have 0 velocities and they must have 0 acceleration, so the following constraint has to hold. Now what we can do is we can solve this first equation for q double dot and insert it in here, which results in the following equation that again must be 0. And now if we solve this for Fc, we get Fc equal to the following. We can then in here back substitute this force into this equation of motion and do some rearrangement. Substitute in all of that a null space projector matrix NC, and what we end up with is the so-called support consistent dynamics. So in essence is a projection of this above equation with NC. And as you can see, this NC times NC transposed times JC transposed is equal to 0, so that made that part dropping out. And this NC is nothing else than a projector which takes equations of motion which have contact forces and projects them into a subdomain where this contact forces drops out and where we have only motion and torque being left. So in this slide we see everything we need. We see on one side the contact force which is a function of the constraint. So given my constraint, given my actuation, and given the current state, we can directly calculate the FC. This is the first element which is important. The second element is that we can rewrite the equations of motion independent of the ground reaction force. And we will do this with a simple example. I again keep up here the support consistent dynamics equations of motion. We have derived for you the equations of motion for the cart pendulum, which has 2 degrees of freedom, which is in contact at point P, and where we have given you the contact Jacobian. Now what we would like you to do is to determine this null space projector matrix and then interpret the capability to move and apply forces by these actuators, similar to what we were doing in the last video segment, but now with the full dynamics equations of motion, where we analyzed 3 different cases. First one where both constraints are active, so X and Y. Second case where the vertical motion is locked, so again P can move like this. And the third one where P can move like this, only in vertical direction.